Every year, the world produces over 1 billion new tires, and just as many worn-out ones end up in landfills. Just imagine, in the United States alone, over 250 million tires are recycled annually, saving the planet from mountains of rubbish. But where do these black rings go after they've served their thousands of miles? They don't simply vanish. They pass through fire, steel, and grinding machines to be born a second time. And what's most captivating, we don't even realize that every day we walk on their second life. Stay till the end, because there I'll reveal a secret that will forever change your perception of an ordinary tire. So today, we're heading to a cemetery of automobile tires. Hectares of land buried under mountains of black rubber rings. These are the silent veterans of the roads, which have rolled their thousands of miles and now lie here, seemingly useless to anyone. But this isn't the end of their story. It's merely the beginning of their remarkable reincarnation. We'll trace how these worn, dirty chunks of rubber pass through a series of brutal yet high-tech trials to be reborn as the soft, springy heart of a modern sports stadium. Americans have learned to give a second life to the overwhelming majority of tires. The recycling rate for old tires in the U.S. currently exceeds 85%. This means that over 250 million tires annually avoid landfill and are sent for rebirth. Part of them are burnt as highly efficient fuel. Part are used in civil engineering, but a significant and ever-growing quantity is transformed into rubber crumb. At this tire graveyard operates a machine resembling a steel tyrannosaurus. It's an industrial shredder. An enormous loader grabs an entire handful of old tires and tosses them into the steel jaws of this machine. Inside it, with a deafening screech, two massive shafts with thick, sharp hooks rotate. They seize the tires with relentless force and tear them to pieces with an incredible crash. Inside every tire is a steel belt, a robust framework of steel wire. During tearing, this belt is released, transforming into a glittering web of steel threads mixed with rubber chunks. This chaotic mixture of rubber and steel moves further along the conveyor. And here, an industrial, powerful, enormous magnet enters the game, rotating above the stream of shredded material. Like a fridge magnet, but 1,000,000 times stronger. It extracts all the steel threads from the rubber mass. With grinding and clanging, the steel belt sticks to the magnet and is dumped into a separate container. This steel will then be sent for remelting, whilst our purified rubber continues its journey. But it's still too large. Next stop, the granulator. During this process, another tire component is released, textile cord. These are nylon or polyester fibers that gave the tire additional strength. These light, fluffy fibers need removing. For this, rubber granules pass through a system of vibrating sieves and air separators. Powerful air streams literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now we have clean but still rather large material. To become stadium surfacing, it needs transforming into crumb. For this, granules are sent for final grinding, often in so-called cracker mills. As a result of this process, we finally obtain what everything started for, rubber crumb. This is a uniform, free-flowing mass resembling black caviar or coarse sand, where each particle size is just a few millimeters. This crumb is carefully sieved to guarantee perfect size uniformity and packed into enormous bags weighing a ton each. Its journey from dirty tire to clean, high-tech raw material is complete. And now, let's transport ourselves to where this black crumb will find its true calling: construction of a new stadium. Workers roll out huge rolls of artificial turf over a perfectly leveled gravel base. But for now, they look dreary and lifeless, pressed against the base. For them to stand up and resemble real grass, they need support. And here, a special machine enters the pitch, resembling a large fertilizer spreader. A process called infill begins. First, the machine spreads an even layer of fine, rounded court sand across the entire pitch. It's heavy and settles at the very base of the carpet, acting as ballast so the turf doesn't shift. And following the sand, our main hero is poured onto the pitch, black rubber crumb. The machine distributes it just as evenly across the entire surface. And here, the main transformation occurs. It's like running on a billion tiny trampolines. This dramatically reduces the load on athletes' joints and makes falls far safer. The final touch is combing the pitch. A special machine with an enormous brush drives across the turf, carefully mixing sand and rubber crumb and combing them deep down to the very base, forcing every blade of grass to stand perfectly upright. And now, when the work's complete, before us appears a perfectly green, springy, and safe pitch. And none of the players running on it might guess that beneath their feet lie millions of particles from old automobile tires. To create one standard pitch for American football or soccer requires on average between 20,000 and 40,000 old car tires. Just think about it. A single pitch completely devours an entire mountain of rubber waste. And how many such pitches are there in the country? Currently in the U.S., there are over 13,000 artificial turf pitches in schools, colleges, parks, and professional arenas. And now simple maths. If we take even the minimum figure of 20,000 tires per pitch, it turns out that in sports pitch surfacing across the country alone, over 260 million old tires have found their new home. Natural turf is a very finicky thing. It needs constant mowing, watering, fertilizing, and giving it rest. On average, a natural pitch can withstand no more than 20 hours of play per week. And a pitch with artificial turf? It can operate 24 hours a day, 7 days a week, in rain and heat. And now about water. One artificial turf pitch can save between 500,000 and 1 million gallons of water annually. That's the amount of water an average family uses over several years. Add to this savings on fertilizers and lawnmower work, and the benefit becomes obvious. Every second, the world transmits over 3 billion gigabytes of data. But do you know that all of this is thanks to a thread thinner than a human hair? And that this thread begins with ordinary sand? Not beach sand, but perfectly pure quartz, where there's only one impurity particle per million particles. To create fiber optic cable that carries light at speeds exceeding 300,000 kilometers per second, you need to journey through chemical vapors, sterile laboratories, a furnace at 2,500 degrees, and lasers that monitor every microcrack. This process looks more like manufacturing a spacecraft than a cable, but it's precisely this that forms the foundation of the internet you're using right now. To create a thread capable of transmitting light at speeds approaching 300,000 kilometers per second, you must begin with sand. But not just any sand, only special, exceptionally pure quartz sand, where the primary substance is silicon dioxide. For fiber optic production, sand with a silica content exceeding 99.9% is used, which means that in 1 million particles, only one particle is an impurity. Just imagine, in every kilogram of raw material, no more than a few milligrams of impurities. And this is critically important, because even a tiny particle of foreign metal can cause light scattering or absorption. And then a signal that should have traveled nearly 100 kilometers without amplification simply vanishes. Raw material for fiber optics isn't simply washed or filtered, it's purified at the molecular level. Manufacturers often employ gas chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and precipitated as the purest vapor. And only then is it converted back into glass. Add to this strict temperature control, humidity, and airflow in clean rooms, and you'll get an idea of how far removed this is from an ordinary sandy beach. Production laboratories resemble NASA's sterile zones more than a glass workshop. And all of this to ensure that every meter of future fiber contains not a single defect. A large transparent glass cylinder, which will later be melted and drawn into an extremely thin thread, is the fiber optic preform. This enormous glass blank is made using a method called vapor deposition. In a large furnace, air is mixed with extremely pure gases. These vapors reach the inner surface of a transparent tube that's heated intensely. When the vapors touch the hot wall, they settle and transform into tiny glass droplets, like dew collecting on a leaf in the morning. Gradually, these droplets accumulate layer by layer until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it closes into a dense solid rod. This is our preform. The preform is placed in a special furnace where the temperature reaches approximately 2,600 degrees Celsius. This temperature is so high that the glass becomes soft and begins to melt, like caramel on a hob. When the preform's end melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and from it forms the finest thread. This thread, the optical fiber, is drawn at speeds of roughly 300 meters per minute. Imagine, that's faster than a cyclist moving through the city. It's important that the thread has the same thickness along its entire length. Optical fiber thickness is typically around 125 microns. This is very, very thin. For comparison, the average human hair has a thickness of around 100 microns. To keep this diameter under control, special instruments are positioned in the process. They monitor the thread in real time and measure its thickness. If the thread begins to become thicker or thinner, the system automatically changes the drawing speed or furnace temperature to correct it. After the optical fiber has been drawn and has become a thin, transparent thread, it needs protection. The fiber is extremely thin and fragile. Therefore, immediately after drawing, it's coated with a special protective layer. The thin thread is drawn from the furnace. After the furnace, it immediately enters a coating machine, a special device that dresses the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. This resembles a small tube or nozzle, inside which sits molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly poured onto it. This coating layer typically consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks. The secondary coating is harder and stronger, protecting from external influences, dust, and scratches. After applying the liquid coating, the fiber passes through special forming rollers. They regulate the layer's thickness and evenness. After the polymer has been applied and formed, the fiber passes through an ultraviolet light zone. Here, under UV lamp influence, the polymer instantly hardens. This process is called polymerization. Those of you who get manicures know how this works. Ultraviolet lamps activate chemical reactions in the polymer. Thanks to this, the coating quickly becomes hard whilst maintaining its elasticity. This is an extremely rapid process. The coating hardens literally in fractions of a second. This method doesn't heat the fiber so it doesn't damage it. The entire machine is equipped with sensors and control systems. They constantly measure coating thickness and fiber feed speed. At the end of all this technological wizardry sits a spool module, rotating with a hum resembling a jet engine sound in miniature. The fiber, resembling transparent silk, lays evenly and precisely coil against coil. The spool moves smoothly left and right with millimeter precision. Around it are sensors, lasers, cameras. They vigilantly monitor that the fiber lays evenly and doesn't twist. With every minute, more and more layers appear on the spool. Imagine, in just a few hours, there are already several kilometers of the finest, almost invisible fiber. And all of this without a single break, without a single scratch. Before assembly into cable begins, fiber from the spool is carefully rewound onto the production line. Since one cable typically contains several fibers, individual threads are combined into ribbons or modules. These ribbons or bundles are then placed into buffer tubes. These are thin, flexible plastic channels that provide the fiber space for micro-movements. This is important because when temperature changes or the cable bends, the fiber slightly expands or contracts. Inside these tubes, gel may also be added that repels water and absorbs vibrations. Around the buffer tubes, reinforcing elements are added. Fiberglass or Kevlar. These are extremely strong threads that protect the cable from stretching. Metal wire is needed for additional mechanical strength. The central rod is a rigid element at the center that maintains the cable's shape. All of this is wrapped with an outer sheath. This is a dense plastic or polyethylene tube resistant to ultraviolet light, moisture, rodents, and temperature fluctuations. The cable is tested. Each fiber's transmission capacity is checked, along with bending strength and moisture resistance. Then it's wound onto large drums, marked, technical documents are added, and it's ready for transport and installation.